This video is about analyzing networks of capacitors when the capacitors are connected in parallel. The first thing to understand about capacitors in parallel is that they all have the same potential difference. This is because there is just a plain wire that connects the upper plate of all the capacitors. Our wires in our diagrams are ideal wires. They are equipotential surfaces. Equipotential means same potential for all the upper plates. Then the wire at the bottom here that's connected to the negative terminal of the battery, that is also an equipotential surface. So the upper plates are all at the same high potential, and the lower plates are all at the same low potential. So every one of these capacitors has the same potential difference. The potential difference of a capacitor is related to its capacitance and the amount of charge on the capacitor. So the capacitance equals the amount of charge, Q, divided by the potential difference on the plate. So if we want to replace this network of capacitors with a single equivalent capacitor, we need to consider the amount of charge on this equivalent capacitor plate and the potential difference or voltage on this capacitor. This equivalent capacitor will have the same potential difference as the battery, which is the same as all of these capacitors. The charge, however, on the plates will be equal to the total amount of charge in the capacitor network, so the sum of all the charges. So this equivalent capacitor has a capacitance equal to the sum of all the charges divided by the voltage. We can split up that equation by putting each Q over V separately. This is just a rule of fractions that you can go ahead and split this up into a sum of fractions with a common denominator. Well, Q over V, that's just the capacitance. So we can rewrite each of the terms in this equation as simply the capacitance of that capacitor. So here is the equation for an equivalent capacitance of capacitors in parallel. This is a little different from resistors. Resistors in parallel use that inverse equation, not so with capacitors. And you can understand why not if you understand the rules about voltage and charge on those capacitors.